Problem 16.6 is a good example of all the concepts in chapter 16. So let's do problem 16.6, or really I should say, I'll do problem 16.6 and you get to listen to me. So that's even more fun because then I get to do it. Yes, lucky me. So here we go. So what we have is this ride. Okay, we're looking down on it, right? It's on the ground, so we're like in an airplane looking down on the ride. And it's 60 RPM, 60 circles per second this way, counterclockwise. They have an arrow there. The radius is 20 feet, and it's being driven by this smaller cog, the smaller 3-foot wheel. Okay, so that's what we know. And here's Michael right here, and I guess here's Aaron a little bit inside in the Ferris wheel. So there's like a horse here and a horse here or something. Okay, so that's what we know. And then we have to answer their questions. So first they say, assume Michael is seated right there. What is his linear speed in miles per hour and feet per second? Let's do feet per second first, then we'll convert that to miles per hour. So part A, we want his linear speed, and his linear speed V is equal to R omega, right? That's one of the formulas that we have. How fast he's actually moving, how fast the wind is hitting his face, is the radius times the angular speed. Okay, we know the radius, that's 20 feet. Which gives us the feet per second. Now we got to figure out omega and radians per second. And they made it real easy for us. Okay, so they said it's 60 revolutions per minute. Well, there's 60 seconds in a minute. So that means 1 circle per second. A circle is 2 pi radians. So it's going 2 pi radians per second, right? 60 RPMs is 1 revolution or 1 rotation, 1 circle per second. 60 minutes, 1 per second. So right away we know that omega is 1 circle per second. A circle is 2 pi radians, so 2 pi radians per second. Now let's say that they gave us a number like 47. Okay, we couldn't do that in our head. So how would we change that to radians per second if it wasn't easy? So let's do that. What you do is you write 60 revolutions, circles, whatever, let's say revolutions per minute. Okay, we want to convert that to radians per second. So we multiply in 1 revolution. We have to have here revolutions at the top, so we got to put that at the bottom. 1 revolution, 1 circle is like 2 pi radians. Okay, they're the same thing. Times, we have a minute at the bottom, so we put a minute at the top. 1 minute is 60 seconds. Now we make sure we did it right, so you cancel. So the revolutions cancel, the minutes cancel, we're left with radians in the top per second, so that's right. And notice the 60s cancel, that's why we can do it in our head. 60s cancel, and we're left with 2 pi radians per second. Okay, so that's how you do it if they gave us a weird number like 47, but if they gave us a nice number, so that's what omega is. Okay, I'm going to turn this off now so we can see better. All right, so let's figure out what the velocity is. It's r omega. We figured out omega was 2 pi radians per second. So it's 20 feet times 2 pi radians per second. So that'd be feet per second. And remember, radians is a natural magical unit. You don't really ever need to write radians or think radians. If it's in radians, your job is done. So it's just feet per second. We don't need to write the radians. So that would be what? 2 times 20 is 40. So it would be 40 pi feet per second. Okay, and we can always multiply that out, 3.14 if we want. I think they even left it in that. Yeah, they even left it like that in their answer. So we could multiply that out, 120 something, right, 3.14. But this is the perfect answer. Okay, so what is that in miles per hour? So we've done this a whole lot, especially in chapter 1, right? That's all we do. So you take 40 pi feet per second. Hopefully you remember that 1 mile is 5,280 feet. 5,280 feet. Feets cancel. Hours, 1 hour is the same as 3,600 seconds. 60 times 60, yep, that's right, is 1 hour. And the seconds cancel and the feet cancel. We're left with miles per hour, so we know we did it right. And they got an actual answer, so let's make sure we get their answer. So they go 40 times pi times 3600 divided by 5280, and that's about 85.679. Let's say 85.68. 85.68 miles per hour, which is pretty darn fast, right? This ride is really whipping around. Imagine going 80 miles an hour in a circle in a merry-go-round. So, maybe a little unrealistic. Okay, what is the angular speed of the drive wheel in RPMs? Okay, now we want the drive wheel, which I turned this off, so let's look at the picture again. Okay, here's our drive wheel. So what's that omega? Okay, it's 3 feet radius, and we know the velocity of the wheel. Okay, the velocity is the same as the belt, right? The belt is going around this wheel at whatever, 45 feet per second, which means it's moving at 45 feet, which means the outside of that wheel is also going 40 pi feet per second, or 85.68 miles an hour. Okay, so that's one of the major concepts, right? The belt is going the same speed, whether it's going around that wheel or this wheel. So that's how we solve this problem, by knowing that. And that's also like 16.8. Whenever you have a wheel driving another wheel, that's one of the things that you use. Okay, so we know omega of the wheel. We know, we know the velocity of the wheel. That's why they had us figure that out, part B. We want omega. What is the angular speed of the drive wheel in RPMs? Okay, so we know that it is, let's use this one. We know its velocity is 40 pi feet per second. We want omega. We know that the velocity is equal to r omega. So omega is equal to v over r. Put the r on the other side. Yep, that's right. So velocity is 40 pi feet per second divided by the radius was 20 feet. So that's just 2 pi. Feet cancel, 2 pi per second, which is what omega is, radians per second. So 2 pi radians per second. But they wanted RPMs. So now we got to go backwards to RPMs, which is okay. So 2 pi radians per second. Oh, wait a minute. Okay, that's pretty easy. 2 pi radians is one circle. Okay, we actually figured this problem out already, right? It's going, wait, no we didn't. Sorry, I did this wrong. It's the drive wheel. It's this little wheel here that we want. Its radius is 3 feet. I was going to say, that's our original answer. Yeah, I know you guys were yelling at me through the video and it didn't work. But maybe it did work because I realized it. The radius of our little wheel is 3 feet, right? Our little wheel here, which I got rid of, our little wheel there is a radius of 3 feet. Its outside velocity is the same, but its radius is smaller. Okay, so now 40 pi divided by 3, that's a horrible number. So I'll just leave it like that. 40 pi divided by 3 radians per second. We want RPMs. So we do the same thing backwards. Let's see, we want minutes. So I put second in the bottom, so I put seconds in the top. 60 seconds is 1 minute. And there are 2 pi radians in one circle. I have radians in the top, so I need radians in the bottom. So 2 pi radians is the same as 1 revolution, 1 r. Radians cancel, seconds cancel. We're left with revolutions per minute, which is RPMs. So you go 40 pi divided by 3 times 60 divided by 2 pi. Whoa, we could do this in our heads. So 40 pi divided by 2 pi. Let's see, the pi's cancel. 40 divided by 2 is 20. 60 divided by 3 is 20. So isn't that 20 times 20? 40 divided by 2, 60 divided by 3. So that's 20 times 20, which is 400. Yeah, so it's 400 RPMs. They always put capitals. I like writing smalls. It's easier to write. Okay, so I get 400 RPMs. And is that, yep, that's what they got too. So it's nice, the pi's cancel, so it's a perfect answer. We didn't have to use a calculator to round off. That's always wonderful. Okay, so the little wheel is going really fast, right? Which makes sense. It's a little tiny wheel. for it to be going fast, for it to be going 85 miles an hour, the outside be going 85 miles an hour, it's got to be whipping around, right? It's got to be going 400 circles every minute, which is like over 6 a second or something. 6 a second would be 360. So almost 7 circles every second. It's whipping around, which makes sense. It has to because it's small. For it to be going fast on the outside. Okay, part C says, suppose Aaron is seated 16 feet. Okay, let's turn our picture back on. There's our picture. Okay, so Aaron is sitting in closer. He's in a horse closer to the middle, right? He's 16 feet from the center. So instead of 20 feet, he's only 16. So his radius is 16 feet. Okay. What is the angular speed of Aaron in RPMs? Okay, this is a trick question. If you're anywhere on the ride, your angular speed is always the same. Okay, how many circles per second you make is always the same no matter where you are. Your linear speed changes, right? Your linear speed depends on the radius, how fast you're actually moving. But as long as you're stuck to the circle, the platform going around, you have the same omega. So they're just checking us here. We didn't fall for it. Angular speed of Aaron in RPMs, so it's the same. So it'd be 60, right? If he's going around at 60, he's going around at 60. So that's real easy. So I'll put C over here. It's kind of hard to read with this writing in front of it. But so right away we know that omega in RPMs is 60, and we know what that is too in radians. It's 2 pi radians per second. So 60 RPMs, same. And what's his linear velocity? Now his linear velocity is V equals R omega. Do they say what units they want? Let's hope it's feet per second. Yes, it is feet per second. Okay, so we know omega is, we already did the math, 2 pi. And we know his radius is 16, so 16 times 2 pi. See, I'll write units here to make sure we get this right. So 16 feet, radius is 16 feet, times 2 pi radians per second. So we end up with feet per second, which is 32 pi, right? So 32 pi feet per second. A little bit less than the other guy, because he was on the outside. He was going 40 pi, because his radius is 20 feet, so a little bit slower. So, okay, makes sense. All right, and finally the last one says, after 0.23 seconds, Michael will be located at S. Oh, wait, it's not the last one. There's a part E in the next slide. Okay, well, whatever. As pictured, Michael located as pictured. What is an angle, POS in degrees? What's the angle in radians? How many feet has Michael traveled? Okay, we better look at that picture. Where's my thing? Here it is. All right, so I'm going to have to scroll up here. We got to look at the next picture under here. Are we going to need any of this information? No, we don't. We don't need part C at all. So I can erase that so we can see what's going on. I'll erase all this stuff. We might need these things. Okay, here is our new picture, and that's all messed up here, but we don't need this stuff. We know omega already. You guys have all this written down. All right, so we want to know what angle it is after 0.23 seconds. So he went from here to here. Okay, so in 0.23 seconds. So that's pretty fast. So what's the angle in degrees? Okay, so this is part D here. And let's see, we have 3 main formulas this chapter. The arc length you go is R. Arc length you go is R times theta, right? Which we know that works if we're doing with radians. As long as it's radians, so 1 radian is 1 radius. The arc length you go, that's the definition of radians pretty much. And then we know that your velocity is R omega, and we know that the angle you go is omega t. Yeah, so we use this formula. We want the angle that you go. So theta is equal to omega t. We know omega is 2 pi radians per second. So 2 pi radians per second times, they said 0.23 seconds. That's just ugly, so let's just get a number for that. So 2 pi, 2 times pi times 0.23, 1.445. So 1.445 seconds cancel. That's how many radians. So, and which is, okay, remember 1 radian is about 60 degrees. 90 degrees is pi over 2, which is 1.7 radians or something. So a little less than pi over 2, right? Pi over 2 is 90 degrees. 3.14 divided by 2. Well, yeah, 1.65, something like that. 1.657, 1.57 radians. We're 1.445, so a little bit less. So the picture looks about accurate. So they did a good job drawing it. A little less than 90 degrees. And what is that in degrees and radians? Okay, they want degrees too. So for degrees, we go 1.445 times, we have radians, I should write my units here. We have radians, so times 180 degrees is the same as pi radians. Radians cancel, so 1.445 times 180 times 180. I just always leave my calculator, so it makes it really easy. It's about 260 degrees. So about 260 degrees. So 1.45 radians, which is, wait a minute. 180, I forgot to divide by pi. That can't be right, right? We know it's about less than 90. So divided by pi, 82.8 degrees. That makes a lot more sense. Good, glad I caught that. So always make sure your answer makes sense. I forgot to divide by pi, and clearly not right, because we know it's a little bit less than 90 degrees. Okay, that looks about right. And then they also say something else. How many feet has Michael traveled? Okay, let's see. Okay, so what is this arc length? S, right? How many feet he's traveled is the arc length. So then we use this formula, r times theta. And again, if we use radians, we don't have to do anything else. So the arc length is r theta. His radius is 20 feet. He's all the way on the outside. Times radians is 1.445. And then we know that we get the right answer. So 1.445 times 20 is 28.9. So he went 28.9 feet. Okay, so that would be our answer for D. So there are 3 answers. This many radians, which is this many degrees, which means the arc length, the distance traveled, is r theta, 28.9 feet. Okay, finally, part E says, assume Michael has traveled 88 feet from the position P to a new position. How many seconds will this take? Okay, so we got to look at the new picture here. So I'm going to erase all this stuff I have up here. All right. It's really cool that I can put the picture up here and draw right on top of it. Saves me from drawing a picture. You guys have to redraw the picture or just look at the one in the text and hope that you can make sense of it. But okay, so I don't think we need this anymore. I hope that I can remember everything because I have to erase it. Okay, here's our new picture. So he goes from here to here. They say the length of the arc is, oh, I can't read it. But it'll tell me. The length of the arc is 88 feet. Okay, so that's 88 feet. So that arc length there, S is 88 feet. Sometimes I say feet, sometimes I put a little slash. It's the same thing. Slash is easier. But then it's weird to write units. Slash per second. That doesn't, well, okay, whatever. So, 88 feet. How many seconds will this take? What will be the angle swept out by Michael? So the angle swept out is this. Here's theta. And how many seconds will it take? Well, let's see. This formula here is theta equals omega t, but we don't know theta or t. So that doesn't help us. We do know omega, right? So we remember omega is 2 pi radians per second. We know the arc length. Oh, so we can figure out theta from this formula. So S, that's equal to, S is equal to r theta. So the radius is 20 feet. So theta is S divided by r, which is 88 feet divided by 20 feet, which is 4 and 8/20ths, which is 4/10, 4.4, right? 8/20ths divided this is like 4/10, yeah, 4.4. So it's 4.4 radians. A full circle is 6.28, right? 2 pi radians, so 4.4, yeah, sure, that looks about right. So theta is 4.4 radians. That's one of the questions they asked, right? They asked that second, and we figured it out first. Oh well. And so that's part, this is part E. I'm doing part E. And now we can use this formula to figure out the time. So if theta is omega t, time with omega in the bottom is theta divided by omega. Now I'm going to turn this off so you can see past all the other writing there. Okay, so theta is omega t, put the omega on the other side, time is theta divided by omega, which is, we figured out theta is 4.4 radians, divided by omega, which we know is 2 pi radians per second. Radians cancel, seconds in the bottom of the bottom is like it's in the top, so that's right. So 4.4 divided by 2 is 2.2, but divided by pi, I'm not going to do that in my head. So 4.4 divided by 2 divided by pi is almost exactly 0.7, 0.70028. So I'll just say 0.7. So about 0.7 seconds. It took 0.7 seconds to go all the way around, there, which kind of makes sense. It's 0.23 seconds for just up to here. So down to here, about 0.7 seconds. Sure, that makes sense. Let's see if they got it right. 16.6, 0.7 seconds. Cool. And 1.4 pi radians. Oh, they left it as pi radians. I said 4.4 radians. Yeah, either way it works. Okay, cool. So that's 16.6. Again, it's a good practice, and just using radians and theta and our 3 formulas that we're going to use a lot. And just remember that they always work well in radians. And if you don't have radians or something, it's just good practice converting degrees to radians and feet per second to miles per hour and RPMs to radians per second. Just be really neat and complete with that. Be really careful. Show all your work, cancel things out like I always do, because I've made a lot of mistakes in my careers. So now I know to stop myself from making mistakes. I try to do it as neatly as possible. On the board, I make more mistakes than I do on paper, though I still do mistakes on paper too, which is terrible. Everyone does, but you got to try all the tricks you can to not do that, because unfortunately it matters. Knowing the stuff, that's important. How to do it, that's the most important thing. But you got to get the right answer too. That's also important. So, okay, enough lecture there. Thank you for listening. Goodbye.